Hey everybody, and welcome to the screencast on the normal distribution, and specifically, we'll look at what's called the standard normal distribution. Okay, so let's get a little bit of the story behind the story. So you may have already had a look at this in your textbook on page 180. There is a particular problem that I think sets the stage relatively well for what we're about to do here together through this screencast. So let me take you into the textbook for a moment. And here we have a particular situation where a mathematics prize at graduation is to be awarded. Okay, and these tend to be, in part, marks-based, but not exclusively. But in the case of this textbook example, they're trying to decide to whom the award goes based on their achievement in math. So you can see that Kaylee has a mark of 84, Lauren has an 83. Okay, so at first glance, 84 being larger than 83, the award should go to Kaylee. But based on previous discussion, which we've had around the topic of how you would make these types of decisions, there are other factors that come into play. Okay, so for instance, if you look at the mean of Kaylee's class, now let me get into the Smart Notebook file so I can annotate some of this information. So if you take a look at Kaylee's class, you can see that there is a mean of 74, and we're reporting a standard deviation of 8. Okay, so given this particular distribution, it looks as though the marks are normally distributed with a mean of 74 and with a standard deviation of 8. Okay, but on the other hand, Lauren's class has a lower mean by about 4 percentage points. So the value of the marks, the distribution of marks X, is normally distributed with a mean of 70, okay, or quite precise 70.0, with a standard deviation of 9.8. So there is a lower average, yet a greater standard deviation. Okay. So reading further along here, you'll notice that the text is prompting us to think about how a comparison that is a fair one can be made. And in this case, it cannot be made, okay, since the distributions are clearly different from each other, that it's too hard to determine that. So what we need to do is to come up with or have some type of index or a standard to which we can compare all distributions, okay, or all normal distributions, and that's something we call the standard normal distribution. Okay? So your note carries on with this. Okay? So the standard normal distribution has a particular notation. Okay, it is as such. Okay, so whatever we're measuring, that is X. So the value in this case of all marks, the distribution of marks, okay, can be somehow compared back to a distribution that has population mean of 0 and then a standard deviation of 1. Okay, so the standard normal distribution always has a mean of 0 and a standard deviation of 1. Okay, so below you can see an example whereby we have a particular normal curve with a mean of 5, okay, and a standard deviation of 4. Okay, so any normal distribution can be transformed, okay, into what is called the standard normal. So every normal distribution, if you do Google it or look it up online, there is an equation that defines the normal distribution, like a curve. So it's a function. There is an equation that defines it. And there actually is a scale factor. There's a factor that scales. So we can take this distribution here that I've outlined right here, and you can transform it into standard normal and vice versa. Okay. So the power behind that is that we can then go back. If we can transform this curve and this one into curves that mirror or are the standard normal, then we can start talking about, well, how far is Lauren's mark away from the mean in terms of the standard normal, and how far is Kaylee's mark away from the standard normal mean? And if we can do that, then we're going to be able to make those types of decisions. Okay? So the idea of finding out how far something is from the mean, what we're going to do is we're actually going to come up with or count and calculate the number of standard deviations above or below the mean. And that is something called a datum's z-score. Right, so let's have a look and see what we can do to calculate how far a particular datum is from the mean, okay, which is called its z-score. Now, what we can do is that for any value x, okay, any value x, we know that its position relative to the mean. So let's take the population mean, for example. Its distance is contingent, okay, upon its relationship, okay, with the average, as well as the standard deviation. And how many standard deviations? Okay, in general, what we'll do is we'll define that as z. Okay, where z is, okay, I want to be clear about that, z is the number of deviations that the datum is from the mean. So we say number of, okay, so z is the number of standard deviations or multiples of the standard deviation, okay, from the mean. So above or below, so it could be either above or below, plus or minus the mean. So what we'll do in this case is if we want to solve for z, okay, that means we can isolate z and we'll have a tidy formula for determining the distance that any datum is from the mean, or its z-score. So by subtracting the mean, okay, so what I'm going to do is we can either subtract it or add it on. It really depends on the sign of the value that we're subtracting. Most text would relate it to being just adding on a particular number of deviations. So we'll disregard the sign for now. We'll deal with that with actually concrete values. If we divide that by the standard deviation, we come up with what's called the z-score. Okay. So to put that into play or into practice, we can actually standardize, okay, these values of x. So when it says determine the number of standard deviations from the mean, we're actually asking you to find the z-score. Okay, so there's a couple ways to say that. So find the z-score, or you could say I'm going to standardize that value, okay, to the standard normal curve. So for an x value of 22.2, what we want to do is recognize, okay, related to the definition of this standard normal curve, okay, so where the mean, population mean is 10, and the standard deviation is equal to 6, recognize already that 22.2, we realize that lies above the mean. So the reason why I'm going there is I really want you to think ahead before solving, and that's going to imply a positive z-score. Okay, so this is just the sense-making part of calculating an answer. Does it make sense? So under that particular premise, let's go ahead and calculate the z-score for an x value of 22.2. So we'll take the value, subtract the mean. The mean is 10, divided by the SD, standard deviation, which I should just write in as a 6 instead of writing the symbol again. It's going to come up to the top right-hand side. So that would be 12.2 divided by 6. And I believe if you calculate that, you would get 12 divided by 6 is 2. And now with the decimal point, I'm looking at the 2/6 left in my division. That's 1/3. So 2.3 is approximately the value of the z-score. Okay, so let's put that into perspective. What does that mean? So this value here means, okay, that x equals 22.2 lies 2.3 standard deviations above the mean. Okay? So already you can start to get a sense that this is a lot more precise than what I was doing before. Because before, recall, we were really focused on whole numbers of standard deviations. So we could very easily count over 1, then 2, then 3, and then use the 68, 95, 99 rule. Okay, so that was easier for us, but it wasn't really opening more possibilities. For instance, what if a datum is not a particular whole number of deviations above or below the mean? Okay, so that's where we're going with this. Now, as far as x equals 10, let's try that out. So when x equals 10, okay, this one here, just recall that the values of x are distributed normally. The mean, right, is 10. Okay, so this here, what we're saying is this is equivalent to the value of the mean. So our z-score should be 0, right? Because it is the mean, it is in the center of the distribution. But just to validate that, let's go through the motions here, and you can see we have zeroed that out. So the mean has a z-score of 0, as it should, because it is in the center of the distribution. Okay? So moving on. So there will be 2 parts to this. This is part 1 of the screencast. There will be a part 2 that digs in deeper, and definitely important for us, as tomorrow there are some school-based activities. So we do want to make sure that we're getting everything that we need to. Okay? So make sure you do pause, take notes along the way, and you might find it helpful without any interactive questions. If you do have questions, then simply text and or email, or take jot notes and come back to class with those particular questions in hand of those things you want to ask. So let's wrap up this part here with this example. So we have the standard normal distribution in front of us. Okay, so there's no standardization, no z-score finding that we necessarily need to do, okay, because we're being told that this is a mean of 0. And for every, let me just write that down here, population mean is 0 and standard deviation is 1. So you can really read the scale quite well, okay, and so on and so forth. Okay, so I'm just going to put these in for reference later on. So our job now, okay, is to find what we're being told is as the following probabilities. So just to reiterate, the reason why we can do a lot of this transformation, so the reason why we can take these bell curves and then all of a sudden transform them into the standard normal is because of the fact that the area under the curve is equal to 1, or the sum of all probabilities, right, which is really what we were doing with our distributions, even in the past unit, is equal to 1. Okay? So that's where we're able to do this, is to hang our hat or our reasoning on that particular fact. So when we go back and we start looking at a problem as such, we're getting into that notion of, okay, so this meaning left, okay, so left of a value of 1, okay, on the standard normal distribution. So we're asking ourselves, what is the probability? What is the area under the curve? What is the proportion of data, of gumballs, if you remember that example, that fit underneath the standard normal curve left of 1? Okay. Well, we know, you and I both know, that because of the niceties around reading these whole number of values, right, we would expect to see 84.1% of all the data lying left of the 1. Okay. Reason why we're doing this particular problem is that not every situation will produce as clean a value as that. So what I'm trying to ask us to do is the following. Okay. So what we're really saying is that the probability that the value of x being less than 1 really is the same as the proportion of data who have a z-score that falls under 1. Okay. So the proportion of data that are less than 1 standard deviation above the mean. So the way we can do that, aside from the 68, 95, 99.7 rule, is to go and take a look at what we call a z-score table. Now this is in the back of your textbook, right at the very back almost. And what it does, let me just scroll up here for a second. You'll notice the title. Okay, it says that these scores correspond to areas below, or an area below that particular z-score. So z-scores that are negative are to the left of the mean or to the left of 0 on a standard normal curve, whereas converse is true. If it is a positive value, it is to the right of the mean on the standard normal curve. So the value we're looking for, okay, if you take a look here with me, okay, either on the screen or take a moment to look at your textbook, is I'm just going to take a screen capture of this. And the value we're looking for, okay, I'm just going to highlight this area. So I'm going to take more than what I actually need, and then I'll highlight that back in the notebook document. Okay, so let's bring that back into here. We'll add a page, copy and paste. So what we're looking for is this. So the z-score, or the number of deviations below the mean, we want it to be 1 deviation below the mean. Now notice there is an accuracy or precision of 1 decimal place here. If we needed a second decimal place, okay, we would then start looking here. So for instance, if the question had been the probability of x, in this case on the standard normal, being less than not just a 1, but 1.01, we would say that the percentage of data, or the proportion of data, the area under the curve, is equal to the following. So we would trace over from 1.0 to 0.8438, because the second decimal point, as we have here, is a 1. So 0.8433 is the 38 is the proportion, which can also be expressed as a percentage. And that's how precise we can get with the z-score table. So we can go back to such a diagram and know that we can go at any particular increment above or below any standard deviation, and we can find the proportion of data that fall to the left. And it's always to the left of any particular z value that you have calculated and have found in your table. Now for us, we're looking for this value here, 0.8413. Okay, so let's go back and fill that in. So here, that would be, according to the z-score table, 0.8413, which we know, by the way, right, 84.1, so to 1 decimal place, it corresponds to what we already know about the normal distribution. So let's wrap this up here with another 2. So let's look at part B. I'll change the color for this to make it a little bit different. So part B. So we're looking for the probability that X falls to the right of 1.5. And in this case, on the standard normal distribution, that is the same as the probability that the datum, okay, will be 1.5 standard deviations above the mean. So we're looking for, here's 1.5, so we need this, okay? We need that area right there underneath the curve. Well, what we can do, okay, is the z-score table only corresponds to proportions that are to the left. So what we have in red is the proportion that is, in this case, less than 1.5. So what we can do is then take all of the curve, that is 100%, and from that subtract away the probability of everything that falls to the left. And by doing so, we'll end up with everything we need to the right. So let's have a look for a z-score of 1.5. And let's go to the table for that. Okay, so we'll go to the table. I'm not going to cut and paste at this point in time. I would ask that you yourself zero in on the 1.5. And if you're looking at 0.9332, you're definitely looking at the right thing. So let's take that back here. So 0.9332, and then we'll just find the difference from that, and 100%. So what are we looking at there? We are looking at 0.0. Let's see here, 668, I believe. Okay, so we're just going to confirm that. I want to make sure that I've got that correct. So I'm just going to add that back on just to validate that. 8 and 2 is 10, carry the 1. 6 and 3 is 9, carry the 1. Same thing. I think we're good to go. 0.668, or about 6.68%. And last but not least, check this out. It's a great question, actually, to train us on how to solve these and how to look at the distribution, or sorry, at the z-score table. We're going to look at the area that falls between -1 and 1.5. So we're really after this area here. Okay. Well, I believe we already have some of this available to us. Okay. So we know already what this area is above. Right? We figured that out. We know that that piece there, previously solved, is equal to, so the proportion of it being larger than 1.5 is 0.0668. Okay. What we have down here to the left, but that is to the left of -1. We have not yet found that. Okay. So if we find that, okay, we can subtract that from the whole, from 100%, and we'll end up with the shaded area. So let's take a look at that. Okay, and by all means, I'm rambling on here through the video, trying to make this concise and informative all at once, but definitely pause and try it out for yourself to see what you come up with as well. So I'm going into the z-score table. We're going to take a look for -1.5, okay, and -1.5 is showing us an area of 0 decimal, oh my apologies, -1 is what we wanted, so there should be a little more area there. So -1.1379, 0.1379, I'm just repeating that so I don't forget, so 0.179 is the proportion of data that are falling to the left of -1. So giving myself a little bit of space. I'm just going to erase part B for now. And looking at part C, so the proportion of data, let's make our communication more formal now. That's equivalent to Z lying in between -1 and 1.5. And we are using the following expressions. We are going to take 100%, and from that subtract the sum of these two areas. So we want to take note of the area to the left of 1 deviation left of the mean, and we'll add on the proportion of data that are going to lie 1.5 deviations above the mean. So let's write in our proportions, 0.1379, adding on 0.0668. And from that, we can come up with a response. So for this here, I'm just going to grab my calculator and let it sort of drive the process. So 0.1379, to which we're adding 0.0668, 0.2047. I'm just going to subtract that off 1, take the absolute value of that, so 0.7953. So in this case, on the standard normal distribution, you can expect 79.53% of the data, okay, to lie in between -1 and 1.5 deviations from the mean. And we can quickly verify that if we add up this, okay, so 68.26 plus half of that, you should get roughly the value we just determined, okay, which was none other than 79.53. Okay. So that's an introduction to the standard normal distribution. What we'll do in the next video is we'll do a very similar process to this final example, but you're going to notice that the values we're using aren't necessarily going to be those that are easily found on the standard normal distribution. So we won't be able to use the 60, 95, 99 rule as easily as we did before. Okay, but we will be using the Z-score table to solve those particular problems.